This video is to show how to use STAAD.Pro to model a bridge deck, and also to showing how to do the reinforcement design in the bridge deck. And today's example is 8 inches bridge deck and with 6 girder lines. And the girder line spacing here is 10 foot 2. Overhang width is 4 feet. We are going to model the bridge deck as a continuous beam with pinned support at each girder lines. Okay, this is the model as a continuous beam with B equals to 12 inches, which is 1 foot strip, and T, which is the deck thickness 8 inches as the section height. So in the STAAD.Pro, we are going to model this continuous beam and open the STAAD.Pro software. First thing to do is do the configure and trying to set up the base unit match the original model. And we have the feet and kips, which is English, and check English, and then OK. The remaining will be default. After that, it will do the new model, and first set up a file name, and you want to do the save the file as bridge design model, deck design model, and choose a folder. Want to save the file. Double check analytical model right here and English unit, and go down to job information. And this job is bridge deck. 1 foot strip structural model. The client, you just enter RIT, and the job name number is the course number. Okay, and then your name. Enter the date. So comment is 12-inch deck strip. Model with dead load and the live load. And we are going to use HL-93 live load for this model. Then create. And this analytical model window pop up. After that, we're going to start with geometry, and from left to right to do each step until we do the analysis. We are not going to use design for this example for any of the structural design. So we'll stop at analysis. Before we do the input, double check the input unit. And right here, we notice that the current input unit is keep inch. Need to change to keep feet to match the original model. So I will go into this input unit button, and then change the length unit to foot and force unit kilopound. Apply. And after that, we are going to check, okay, this input unit change to keep feet. And after we confirm the unit match, and going to each coordinate. So we are going to have 8 nodes, so which is 1, 2, 3, 4, 5, 6, 7, 8. So we're going to use this coordinate to put each of the nodes to generate this continuous beam. So 0, 0, 0 for the first one. And 4, 0, 0 for second one. And the third one is 14.167. Next one is 24.333. and 34.5, 44.667, 54.833, and the last one is 58.833. This represents the total bridge stack width. So after we create every node, we do want to change the view to 2D view. So go into the view button and turn this front view active like this, and back to geometry. And we're going to show the nodes as well as the node number. So going to do the right click, labels, and check node number, node points, and apply. Click OK. So next step, we are doing the add beam button right here to connect each node. Okay, and escape. After you connect all the beam members, escape. So we're done with geometry. And going to the properties. And this property is going to be a concrete section like this. So which the width equals 12 inches, which is 1 foot, and the depth is 8 inches, equals to 0.667 foot concrete. So going to use define and going to rectangle. YD is the depth. So we're going to use 0.667. And ZD is the width, which represents 1 foot strip. Material concrete. And add. Close. So you will see this rectangular concrete section showing in the window, and highlight that, assign to view, assign to all the members that are currently in the screen. So done with properties. And next step, I'm going to check material, just to make sure that every member has a concrete material. Okay. Save your model frequently. There's no specifications for this continuous beam model. We can skip that step and go into supports. And for supports, we're going to set up the pinned support represents the beam or girder to deck connection. So create a pinned support right here, add, and highlight the pinned support and use cursor to assign to node 2, 3, 4, 5, 6, and 7. Escape. So done with support. Going to loading. And for loading, we are first need to identify those dead load cases. So moving down for this handout. And for the dead load, we have DC1 represents the deck self-weight. And this weight equals to density of concrete, 150 pounds per cubic foot, times 8 inches, divided by 12 inches per foot, and times 1 foot strip. And this is a uniform load on a continuous beam model, equals to 0.1 kg per linear foot. And DC2 here represents the stay-in-place deck form, 15 pounds per square foot, and times 1 foot strip, and equals to 0.015 kg per linear foot. Okay. So if you take a look at the plan set, And this stay-in-place stack form represents the weight in those stay-in-place stack form additional concrete in the ribs. So we can find the nodes right here. Um, See the concrete stack slab um, shall not exceed the weight of 8 inches slab by more than 15 pound per square foot, using the 150 pound per cubic foot density. So the additional concrete in those areas beyond the 8 inches stack is 15. So that represents the DC2. So next one is DW is a wearing surface, represents the deck overlay and utilities. So we have the 38 pound per square foot HBP deck overlay and plus 5 pound per square foot of utility and times 1 foot strip equals to 0.043 kip per linear foot. So this is the wearing surface. We're going to input those load in the STAAD model. For load case details and add, the first one is that load and title is DC1, represents the deck self weight. And the second case, we do the DC2, represents stay in place deck form. The third one is DW, wearing surface, close. And for DC1, we add load items, highlight DC1, add load items, do the member load, and uniform force. W1 is the magnitude, so we're going to use negative 0.1, and negative represents the downward direction. Upward Y right here is, so positive Y is upward, represents this global coordinate, and GY is global. Check GY. And D1, D2, and D3, if the uniform load occupied the entire member, we just leave those as zeros. Okay, and close. And then we highlight this uniform load and assign to, use cursor to assign. Assign to each member. Okay, and done with DC1, and highlight DC2 and add member loads and using negative 0.015. This is the stay in place stack form, and in the GY direction and everything 0. Close, and again assign to each of the B members. Escape. Then highlight DW. This represents deck overlay and utilities. And just add member load, uniform force, and negative 0.043, and global Y direction, and add. Close, and highlight that, assign to each B member. Escape. Save the model. So we're done with the dead load cases. And so next step will be the live load. Okay, and for the live load, we are using one axle load, which is 32, the axle load for HS24 for truck, like that. So we have the design track and just pick one axle right here, the 32. And each wheel will be 32 divided by 2, 16 caps, and space at 6 foot. And we will let the truck moving transversely on the deck to represent any possible locations of the truck and to figure out what is the governing load generated by the moving truck for live load cases. Okay, so we will try a 1-lane loaded case, 2-lane loaded case, 3-lane loaded case, and 4-lane loaded case. So we're going to do the multiple cases for this bridge deck width. So the overall is 58, 10 inches, and minus the barrier width, clear roadway divided by 12 foot, and we end up get 4 design lanes for this bridge. So we're going to try doing the 1-lane loaded case and 2-lane loaded case, 3-lane and 4-lane loaded case, and then make those trucks moving across the entire bridge deck. And for the 1-lane loaded case, we take the 16 wheel load, space at 6, and use 1.2 multiple presence factor, which is right here, single lane loaded, and this truck just moving across the bridge deck. And for that, we also need to consider the dynamic impact for the deck design. Then we're going to use 16 times 1.2 times 1.33 and equals to 25.536 K. And this, the wheel load will represent just one axle load. And later on, we will divide by the equivalent strip width and based on the AASHTO design code. And if you take a look at this table, and we're going to divide by the equivalent strip width to get the live loads per foot. So it ends up get the live load per foot using the equations here. S here is the girder spacing in foot. So the concrete that cuts in place, if we do the calculation, the positive moment, which is bottom in tension, will equals to 26 plus 6.6 times girder spacing, and we end up get 93.12 inches divided by 12, get 7.76 foot. So the 7.76 foot will be the equivalent strip width to carry one axle load. So after we use the one axle load here to calculate the live load moment, we will divide by 7.76 to get the live load moment per foot. And for the negative moment over the support or over the girder, and we are using 48 plus 3.0 times girder spacing, and ends up get the 78.51 inches, and divided by 12, get 6.54 feet. So after we get the output from STAAD, and we're going to divide it by 6.54 to get the live load per foot, and combined with the dead load. So this 1-lane loaded case, we are input this truck load in the STAAD. To define the moving load, we are going to use the definition and the vehicle definition. Going to add the vehicle reference 1, this 1-lane loaded, and the width is 6. And the wheel load. Okay, first wheel load, based on our calculation, is 25.536. Second one is 25.536 space at 6. This represents that a pair of wheel load and to add. And type 2, we are going to do the two-lane loaded case. Okay, so the two-lane loaded, we have the truck, the first truck and the second truck, space minimum 4 feet, and this represents, in this situation, you have two trucks side by side and moving across the bridge deck. So we're going to do this. So this have a 4-point load, and those are spacing between the points loads. And we have a two-lane loaded case. So if you take a look at two-lane loaded case, multiple presence factor is 1. And then we do the dynamic impact again. So 21.28 is each of the wheel load magnitude. So going to do this. So the width of the truck will just keep 6 for just for one truck. Okay, so we will put 21.28, 21.28, and space is 6. So in order to create a new row, hit enter and get 21.28 and space of 4 and hit enter again. 21.28 and space 6 right there. So this is the 4-wheel load represents 2 trucks, and this 2 truck space at 4 and to add. And type 3, we do the 3-lane loaded case, and each truck width is 6. And load for each wheel load. Now we have the first truck right here, and second truck space is 4, and third truck space 4. And so this is the layout of the wheel load. And 3-lane loaded, we need to consider the multiple presence factor 0.85, and also consider the dynamic impact. So we get the every wheel load will be 18.088. The first track, 2 wheels, and hit enter, 18.088, space of 4, 18.088. So this is the 2 tracks. Third track, okay, so 6 wheel load. And after that, we do add. And the last one will be a 4-lane loaded case. And we will consider the 4 trucks side by side and moving across the bridge deck. So those are the wheel loads and times 0.65, and this multiple presence factor right here for 4-lane loaded. And dynamic impact 1.33. So each of the wheel load will be 13.832. Width is 6 for the track wheel load. Okay, so we'll put 13.832. The spacing between tracks is 4, and wheel spacing is 6. Just hit enter to create more rows if needed. Okay, so we're done with four-lane loaded scenario, so which is the maximum number of lanes that this bridge can accommodate. So after we create those vehicle definitions, and we are going to do the load generation. So going to the load case details and do the add. So we are going to do the load generation for the moving load analysis. So first, we need to determine how many loads that load cases we would like to generate. And this actually depends on the X increment or the moving load increment and what's the step size you want to set for this moving load. And again, um, so it's up to the designer to determine the increment. And you can make the increment small, and the smaller, the more accurate. But on the other hand, it will create more loading cases and slow down the calculation time. So usually we can start with like 5%, like like 1%, like 1% of the total bridge length, or so as a like 1% as starting point, and you can definitely make it smaller and make it bigger. The course steps will end up like less number of steps, but you end up a faster calculation speed. There is some balance between the step size and also the calculation time. So for example, that we set this the moving load increment 0.2 feet, okay, right here. So the number of load cases you generate to cover the entire bridge width or the deck width for the moving load will be the clear roadway minus 2 feet um, and minus 2 feet from the inside face of the barrier and minus the total truck width, okay, from the first wheel load to the last wheel load and divided by X increment plus 1. So this is the adequate number of cases to cover the moving load from left to right of the entire moving range. So let's take a look at that. So means that the truck will start 2 feet from inside face of the curb. So this is the first wheel load start. And then this truck will start moving from left to right until reach the other side and from 2 feet from the inside face of the right curb. So stop right here and just the whole moving range of the truck location. And during this process, we want to identify what is the maximum moment created by the truck moving in this bridge deck. The positive is somewhere that in the middle of between the two girders, and negative moment is over the girders. Okay. So first, if you decide, okay, so like to use 0.2 feet as a X increment, and we are going to create the number of load cases, use the clear roadway minus 2 feet, and minus the truck width, which is the first wheel load to the last wheel load, which is 6 foot right here, divided by X increment plus 1, we create 230 cases. So after that, we generate 230 cases for the one lane loaded case. Okay, so you see it right here. And the two-lane loaded case, we're going to generate the live load cases for this two-lane loaded, which is the clear roadway -2 feet, and -16 feet from first wheel to last wheel right here, and divided by x increment plus 1. So should be 180 for the second case. Okay, just add right here. Okay. And 3-lane loaded case, we are going to use the clear roadway width -2 feet, -2 feet, and -26. So this represents from the first wheel to last wheel, and this the entire width is 26 divided by x increment 0.2 feet and plus 1 is 130. Just add, you see here. And the last one will be the 4-lane loaded case. And we're going to use the clear roadway -2 feet on the left, 2 feet on the right, and then minus the total track width from the first wheel to last wheel. This is 36 divided by x increment, so which is step size for the moving load, 0.2 feet plus 1. So we get 80 here. Just add. Okay, after that, close this window, and we need to assign those load cases we created to each of the vehicle, type of vehicle. And for the first 230 cases, highlight that and add. And we are going to use, okay, so this 1, 2, 3, 4 represents the vehicle you defined here. Okay, we are going to use type 1 is 1-lane loaded case, and initial position of the load. So where is the first starting point for the wheel load? And this will be right here. Okay, so this will be 3.5, which is 2 feet from inside face of the barrier. So if you take a look at that, it's 2 feet from this point. So that's the starting point of the moving load. And we have the barrier is 1.5 feet, and plus 2 feet, that's 3.5. The y00x increment right here, so it's important to match your model. We chose 0.2 feet right here, and to add. Close, and then highlight the next 180 cases, which is for 2-lane loaded, and choose type 2 vehicle right here. And starting point is 3.500 for the wheel load. Again, x increment 0.2 to cover the 2-lane loaded case. Close. Highlight the next 130 cases right here and choose type 3. And x coordinate for starting point is 300. So right here, the starting point, like x increment is 0.2. And the last one is 80 cases here for the 4-lane loaded. So use 4 and 3.5 and x increment 0.2. Do add and close. So after we done with the truck load, the loading generation, so next step, we're going to do some of the combination. So we are going to do the dead load strength combo, which is 1.25 DC plus 1.5 GW, and this dead load combo for strength 1. And we are going to define the service combo to get the service moment, which is 1.0 DC plus 1.0 DW. we're going to do that. So do the load case details, highlight that, and do add. And this time we define combination right here. And I will call the dead load strength combo. And then doing DC1 is 1.25 and add, okay? And DC2 1.25 here, add. And GW is 1.5 and do add right here. Then we have this one, okay? So this is dead load combo. And we are going to define a dead load service combo. Just everything is 0 or 1.0. Okay, just for dead load, add that. So close. And for loading, the next one that we're going to do the load envelope. Because the moving load, you see that there's several hundred of load cases, right? So it's over 600 cases, and we're going to identify the governing one for the live load using the envelope, load envelope, and highlight this load envelope add. And so this just type envelope 1, just type none. And we're going to highlight, okay? So for the live load, just right here, from live load, case 4 to 623. So to highlight those and going to the right, selected. So you see the selected from load case 4 to 623. And we add this one is just to identify what is the governing live load moment. So just add. Okay, so we're going to see this envelope and close. So down with the loading assignment for this Savior model and going to analysis. And analysis window pop up and doing the define command, we choose no print, okay, and do add to see the perform analysis command here and close. And save your model and do the run analysis. So we are target 0 errors and just ignore the warnings for that. And we're going to do the go to post processing mode. Click OK. And so we are going to find from this output is the beam results. Okay, so we're going to beam results. Want to take a look at the moment for dead load strength combo, and this is the moment shape for strength combo and service combo. And we are going to take a look at the envelope, which is the live load moment. Okay, so we are going to take a look at this. Is it clear to see all the results from the layout and do the graphs? Okay, we notice that here showing the keep inch for moment. So want to take a look at keep feet, right click and go into the display options from the menu and choose force unit and change the moment to keep feet. Okay. Distribute force, keep feet. Okay, so just apply and you will see the changes right here and click OK. So we're going to take a look at first right here showing the combination dialogue combo, and this is the 1.67, and just click each of those, okay, each of the B members. So we have the STAAD showing the bending moment on the tension side. So here 0.944 should be positive moment because it's bottoming tension. Here is negative 1.67 is top intention. Top intention is negative. Okay, bottoming tension is positive, and STAAD convention is draw the moment diagram on the tension side. Okay, so we checked here is one negative is 1.83 and positive is 0.883. Here 0.904. Okay, so this 1.83 is 3.944. Okay, so from that we check each of the members and then take a look of the output. So we end up get the dead load combo for the strength combo is 0.944 for the bottom intention and 1.83 top intention, which is negative from the output. And then the unfactored load combo, we are going to use the right here is the combination service combo. Okay, service combo. So we will check each one by one. So this is negative 1.26, the top intention, and here 0.716, 1.39, 1.39, 0.67, 1.36, 0.68. Okay, so we do identify the maximum. So we have positive 0.716 and the negative top intention 1.39. So put those things, okay, just in the summary is right here. Okay, 0.72 and 1.39 for the top intention. Okay, and we are going to find output from STAAD is a live load envelope. So it's unfactored. It's unfactored. So we didn't specify the load factor. So going into there, and from this result, and see envelope right here. Okay. Again, we will check those one by one. So this is focused on the moment. So this is 12.8. Here, the second member, we get the top intention is 48.9 and bottom intention is 53.4. Okay, next one, 48.9, 42.9, 44.9, 42.9, and 44, 48.9, 42. Okay, so after we check each member, and we do identify that for the top intention is 48.9 and bottom intention 53.7. So we're going to use those. Okay, so this output directly from the output of STAAD and put in the summary sheet. So so after that, This the output is for the one axle load. Um, we talk about using the equivalent strip width, and this is the equivalent strip width ends up handle the one axle load. So we're going to use the equivalent strip width, which is calculated at the beginning right here. So the positive moment we have 7.76 and negative moment 6.54. We're going to use those and um, divide by the equivalent strip width right here. Um, so we are using the positive moment 53.75 divided by 7.76 and get 6.93 kip feet per foot strip, and negative moment use 48.9 divided by 6.54 and get negative 7.48 kip feet per foot strip. So after that, those are unfactored, and we do the load factor for live load of the strength combination 1.75 and use 1.575 times the service load and get the factor load. After that, so we are going to do the load combination, um, including both dead load and live load. So we have the positive factored strength 1 moment is 0.94 for the dead load strength combo and plus 12.13 for the live load, including the 1.75 load factor, and gets 13.07 kip feet per foot strip. And this is the governing bending moment for bottom in tension. And negative moment equals to negative 1.83 plus negative 13.09 and get negative 14.92 kip feet per foot strip. And this is the governing moment top in tension per foot. And unfactored, we just use the unfactored dead load combo, service combo plus unfactored moment, live load moment, and get positive 7.65 and negative, and we get negative 8.87. So those are service design moment. Okay. So after we identify those design, the maximum moment demand, and we're going to design the reinforcement using the reinforced concrete design. So we will check the strength of reinforced the top and bottom rebar, the main reinforcement, basically check against with the maximum positive moment that we calculated from structural analysis and top main reinforcement, and we'll check against the maximum negative moment just overlook here. So take a look at the design here. The top main reinforcement is the transverse reinforcement on the topmost, right? Uh, um, those are the main reinforcements on the top, main reinforcement on the bottom, and those reinforcement is designed for to resist the maximum bending moment we calculated from our structural model. And longitudinal rebar, so those the top rebar is the temperature shrinkage, and the bottom longitudinal rebar, those are the distribution steel. So if we take a look at the summary right here, we talk about those 4 layers reinforcement. The bottom main reinforcement is based on the maximum MU right here, just based on what we calculated from STAAD model, right? The bottom reinforcement and top main reinforcement, the transverse direction is based on the maximum MU. And the longitudinal direction on the bottom is called distribution steel, and usually take 2/3 of the bottom main reinforcement, and top rebar is the temperature shrinkage is based on the minimum reinforcement ratio. So the original plan here, we have the the bottom reinforcement is 5,584 at 6 inches, and this represents the first number 5 is number 5, and 584 represents the bar length is 58 feet 4 inches long, and that's based on the total bridge width, and each side will leave us 3 inches clear. So that's the 58 4 inches for total bar length, and first number 5. So number 5 at 6 inches for the main reinforcement on the bottom, and top is 5, number 5 at 6 inches on the top main reinforcement. And for the bottom distribution steel, use number 5 right here. So number 5, the distribution steel between the girders and top rebar, the longitudinal rebar also use number 5. So we will check the number 5 at 6, and for the bottom main reinforcement, and the strength we calculated based on the reinforced concrete bending strength equation, and we get 16.1 kip feet per foot strip for the bending strength greater than 13.07, and top reinforcement we get 16.1, and also over the 14.92, which is the demand that we calculated. So we check those rebar design meet the requirement. And after meet the strength limit, and we also need to check the rebar, the maximum reinforcing ratio based on C over D ratio less than 0.42. That makes sure that this member is tension controlled. Okay? So C is the dimension from the topmost fiber to neutral axis, and D is from topmost fiber to the rebar, the centroid of the rebar on the bottom. So I will check that, and we also need to check the minimum reinforcing ratio, and based on what's the bending capacity this rebar can provide, and greater the minimum of the two. One is 1.2 times cracking moment using the modulus rupture times the section modulus, and the other one is 1.33 of the maximum moment demand, which is MU. So minimum to meet the requirement. So this one is cracking moment governs. And we also need to check cracking control this service limit. So make sure the stress in the rebar not greater than 0.6 times the yield strength of the rebar, which is 0.6 times 60 KSI 36, and make sure is the crack is not too wide, is within a controlled range. Okay. So after we check all of those requirements, and then make sure the longitudinal, which is secondary reinforcement design, meet the requirement, and the bottom distribution steel just to take the like roughly 2/3 of the main reinforcement on the bottom, and we have so like 220 divided by square root of space, the girder spacing, and 2/3. So we end up get 69 is 1 governs. And using the main reinforcing steel, and number 5 at 6 inches, you end up using the rebar table, so number 5 at 6. So we are going to use 0.31 times 12 inches divided by 6 inches spacing. So this is the rebar area per 12 inches strip. Okay, so number 5 at 6 is 0.31 times 12 inches divided by 6 inches, so 0.62 inch per foot, and times 69% for the longitudinal ratio and get 0.43. So we are going to use number 5 at 8 inches for the bottom longitudinal rebar, and top the secondary reinforcement is temperature shrinkage based on the minimum reinforcing ratio. And usually, so this it will put nominal steel on the top longitudinal direction. So we're going to use number 5 to be consistent with the remaining of deck reinforcement size. And so although we have the maximum spacing 18 inches specified in code, but in practice, usually we use 12 inches to control the cracks. So usually the top longitudinal reinforcement use number 5 at 12 inches meet the temperature and shrinkage requirement. Okay. So that's all for the model.